In this video, we'll be discussing the role that statistics plays within the storytelling process. So, as before, statistics seeks to summarize the data using numbers or quantitatively. For example, rather than reading through a whole data set to try to figure out what typical values are within the data, we could provide an average, a mean, or a median, depending on what our questions are. The goal is then to select statistical values or statistical techniques that address the questions or purpose of our story. Now, as we discussed in the previous video, starting from a fixed purpose is actually very important. And I'm going to call those through these lectures or this lecture set the research questions, the questions that are set out to be answered by the research. But ultimately, they relate to the purpose, the goal of the story that we're trying to craft. So when we're picking our statistics, it's important to always reflect back to what the goal is to determine what the appropriate statistic is to select. So let's talk through a quick example. This is kind of a famous example. The average current salary of program graduates out of a program for 1 year of graduates out of a program out of North Carolina. If I calculate the mean salary, it's $250,000 a year for these graduates. And if I calculate the median salary, it's $28,000 a year. Which is right? Well, again, going back to the previous point, it depends on the question that you're asking with these statistics. So we seek to select ones that tend to answer the question. And the truth is that from this perspective, in a way, they are both right in that they're both calculated mathematically correctly, and they both accurately tell the story that each of these distinct values are trying to communicate. As before, this might be an unexpected finding, so we dig deeper. We find out that within this program, in this year, we had a graduate named Michael Jordan, and that his salary is very, 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 very high. And when we look at that, that helps to explain why the mean, which follows outliers much more, is much different than the median, which is much less impacted by outliers. Note that this doesn't mean that in this case the mean, the statistic, is wrong or incorrect. It just means that it's telling a different story. And so in determining these, we would have to ask, what story are you trying to tell? Are you telling the story of this class, this specific year in this specific program? Well, if so, the mean is an accurate description of that we did have individuals who had smaller salaries and one individual with a much higher massive salary, that the median would be missing. The median wouldn't be representing that individual with the massive salary. On the other hand, if you're trying to, say, predict for the next year, well, we might have the case where we're not going to have that person with that massive salary next year. So maybe the median is a better prediction for the next year. Or maybe what you're trying to do is tell the story about what's being represented. The mean is the value that's closest to all the numbers, but the median is the 50th percentile. Maybe you're trying to say this is what about half of our graduates make. About half of our graduates make $28,000 a year, and maybe that's what you're trying to communicate. And if so, then you would use the median because that is what your question is about. That's what the purpose of this is about. Going back to what we talked about in the last lecture video, this deeply relates to starting with the purpose of telling the story of the data, not saying what you presuppose or want it to say. You're trying to say what the data say. And there's a big difference here. So consider If I was a professor in the program trying to sell my program to students, then maybe what I would do is I would advertise the mean salary. But again, that wouldn't be an accurate or that wouldn't be a particularly accurate representation of this data for the purpose of saying this is what future students in the program could earn. That would be a deceptive use of statistics in that case, because that would not be a good guess of what future students in the program could earn unless they also became NBA sports stars. For most students, or excuse me, for the students who are going into the program who are not NBA sports star, this is actually a drastically deceptive figure, or a drastically incorrect figure, I should say, of what they would earn. So ultimately, again, it depends on the question. If you're trying to study that class, there's no use denying that Michael Jordan was a graduate. And so in that case, it may be useful or positive to have something that's showing that. Of course, if you're studying something different or trying to predict future classes, then maybe you want to look at this in a different way and would choose to use a different statistic to represent that. Ultimately, our goal with statistics is to provide this quantitative summary. And some view this as being more, quote, objective in some way because it's based on data. And if you're ever tempted to think that, and in some ways it is, but if you're ever tempted to think that this is purely objective, consider this example and my selection of which statistic to present, and realize that that selection can bring a massive bias to the reporting, maybe even made all the more insidious because it seems objective to many. But my presentation of geography majors from the 1984 class of University of North Carolina making $250,000 a year, that is not an objective presentation of our data. I really like this comic. I'm sorry, I just had to have a place to put this in. And this point of outliers is kind of a bit of an aside from this lecture and the purpose of this lecture. The last point is meant to be, with Michael Jordan, is meant to be, use statistics that reflect your research question. On the other hand, the broader point of outliers is also itself important, and outliers do often play a role in how we approach our statistical storytelling, what methods we use, etc. And you know what? It's not really clear what we do with them. I feel like a lot of classes and textbooks just kind of say, hey, note if there's an outlier, and don't really talk about that more in depth. So rather than just ignoring them and hope they don't appear in data, and of course, outliers appear all the time, let's actually have a bit of a discussion about them, just acknowledging that this is a bit of an aside. So let's jump in here. I like that, outlier. And actually, let me go back to this figure because I think this illustrates the thing that we don't want to do. And we'll talk about this more in depth in just a second. But you don't want to erase a data point that's a genuine data point that just disagrees with you. Again, that is a symptom of approaching data with your hypothesis and trying to force data to fit into your hypothesis. You make decisions like this that might seem like they make sense to you, but if you write this down and present this to an objective third party as part of your results, if you are open about your reporting, this is going to really undermine any conclusions that you make, because what you're doing is erasing your data to fit your theory instead of changing your theory to fit data. So outlier or outlier. So let's talk about this. Let's have a real conversation. What do we do? Well, my suggestion is to first check into them. And this is very similar to the suggestion that I made. And I think this is always a good default suggestion. When things aren't happening the way you expect, look into it. Like, don't just accept it. Don't just do some dogmatic thing of, oh, I have to believe data, so you forget about everything you've ever known in your life. Or, oh, there's an outlier, so we have to remove it. Or, oh, there's an outlier, so I have to keep it. Don't be dogmatic about it. Seek to understand what the heck is going on here. So check into it. With outliers, one important thing to check into it and see if there's an error. Was it a typo? are the values on the different scales. I was recently working with a study that had data from, I think we were studying 13 or 14 different hospitals. And one cluster of 3 hospitals reported their data, and all of their data were just way out there. They were just way different than everything else we were seeing, and they all looked like errors. And one of the collaborators said, "Oh, we some computer error. Let's just throw out this." And what it turned out to be was, I guess, in a way, a computer error. I think it was somehow that the height or weight had been withdrawn from the computer reported in metric system rather than imperial. So we were expecting this to be in pounds, and it was actually in kilograms. And so everybody in the study from there was just like weighed absolutely nothing in comparison with all the rest. And it just looked like this massive chunk of outliers that nobody could figure out. But on looking into it, we figured it out, and we correct the typo. So in the case of outliers where there was an error, we just fixed the error and then reassessed to see, is that still an outlier? And of course, if it was an error, then there's no reason to believe that would be an outlier once it's been fixed or addressed. So checking into that, I think, is a good first step. Now, if there's not an error, if this wasn't a data entry error, if this wasn't an error of scale or something like that, then the second thing we do is to consider what story this is telling us. So we have an individual or several individuals who represent outliers. We've confirmed that these are not errors. Let's figure out what's going on there. Why is this individual an outlier? Why are they so different to these individuals? Why are they so different from the rest of the group? And what you might find is that that individual or these individuals represent a subgroup. Now, in that case, I was working on a study where we were looking at individuals, and we had a group of individuals who were considered in the data, and they just had way worse outcomes than everybody else. And we were trying to figure it out and realized that these individuals had an extraordinarily high risk and were in the hospital for a completely different reason than the rest of the population. And that brings up an interesting question. Now, these individuals were, I'm not quite sure how they were initially admitted into the study, but this group of patients, the question is, should they even be in the study in the first place? And in that particular instance, the answer was no. We don't know how they got in the study in the first place. And the study wasn't something that could be harmful, but it was something that having this subgroup in that study was not what we were attempting to assess with the study. So it's not that they shouldn't be in there for harm to participants or anything like that. It's just that in our study, we're seeking to evaluate this on the a certain population of patients, and to include this other population can have results that are drastically different than our population that we're intending to study. So in that particular case, what we can do if it's a subgroup, there's 3 options. One is to ignore the subgroup if that's what you find. I highly recommend not doing that if you find that all the outliers belong to a subgroup. The second option is to account for that statistically. So you would make a group A and group B, representing which group the individuals belong to, and you could include that and account for that statistically. That has some pros and cons, and if you are convinced that the effects affect both subgroups equally, then that makes sense. But that's an assumption that'll be made with many statistical methods if you make groups, is that the relationships among the variables are the same within each group. And that may not be true. So if it's a subgroup that's really not what you're intending to study, what you may do then is say, okay, for the individuals in the subgroup, they are not who I'm intending to study, so I'm going to remove them. Now, I want to be careful here, and this is important. You don't remove the outliers. You remove the subgroup. So if other individuals who are in the main chunk of data are also in that subgroup, all of those individuals get removed too. That's what this option is. And it's a very reasonable option, again, if it's a subgroup you're not intending to study or a subgroup that you didn't realize was in your population in the first place. Within this, you would make sure you clearly document. And again, that goes back to one of my fundamental rules here is you can do whatever you want as long as you have clear documentation. So you would clearly document that this happened. Be open, like don't hide it in the bottom of a table somewhere. Be open and honest so everybody can see what you're talking about, what you're doing. Make sure everybody understands. And then as part of that, you implement this population clarification. We're saying we're looking at population A, and that does not include this subgroup. And then you remove all the patients from that particular subgroup. So that's one option. Now, I want to also specify here. Let's say I have a group of 3 patients, and they are a group of 3 patients who are outliers. They are not in a subgroup just because they're outliers. They could be in a subgroup because they're the only males in a study of females. They could be in the subgroup because they're the only people in this ward and everybody else is from a different ward. They could be a subgroup because they're NBA stars and nobody else plays in the NBA. Like they could be, there's legitimate reasons they could be in a subgroup, but just being an outlier is not itself a subgroup. The subgroup is a demographic classification of them that's independent necessarily, independent of their status as an outlier. That is, their demographic classification is the subgroup we're looking at, not whether or not they're an outlier. The outlier status is not a valid subgroup for considering for removal. In this case, we'd be looking for something independent or different than that. I shouldn't say independent. That means something slightly different, but something different than just the outlier status when we're determining subgroups. So be careful of that. Again, just because you're an outlier, that doesn't mean you get removed. And actually, I guess that comes to our final point, which is if it's not a subgroup, keep that data point in, you can present it both ways with that data point in and with it out. But you don't just get to remove data because you don't like it. Just because it disagrees with your theory doesn't mean you get to remove it. Again, consider your research questions, consider what populations you're intending to study, et cetera. But you don't just get to remove data if you don't like it. So you can check, see if there's an error, then look if it's a subgroup that should be in the study or shouldn't be in the study. If it's a subgroup that should be in the study, consider accounting for it statistically, and then your outliers may no longer be outliers after they're accounted for, after the subgroup thing is accounted for. And if it's not a demographic difference, or if you can't find a reason that's connecting your outliers, then keep them in. And it's just something to present, or even something to highlight about the data. Hey, these individuals are different for some reason. Connecting this back to kind of the inciting example in this lecture video, the Michael Jordan case, if I were determining as to what to do with Michael Jordan, I would really consider what the research question is to figure out, is it meaningful to keep him in there? So if the research question is trying to discuss the center as defined by the median, it doesn't really matter anyway. If it's looking at the 50th percentile, if I was looking at a research question that was mean specific, or intentionally using the mean for some other reason, I'd go through the steps. First, I'd check if it's an error. No, it's not an error that Michael Jordan made however many millions of dollars that he made. Check if it's a subgroup. Well, that could be the case. It's a subgroup of individuals, and maybe what I find to define that subgroup is Michael Jordan is an individual who is not working in a career in his major. So maybe that's what I use. I say, okay, well, because his career is not in his major, he shouldn't be included. But note that if I say this, and that's the subgroup I exclude, I can't just remove Michael Jordan. I have to go through the rest of my data set and figure out, is there anybody else who is in a subgroup or is in that subgroup? Is there anybody else who works in a career that is not from their major? And if so, all of those other people have to be removed too. So if I define the subgroup, that might instigate the removal of the outlier, but it also may instigate the removal of other participants as well. And I do need to check and make sure that everybody from that subgroup is removed. Now, if it isn't an identifiable subgroup, leave it in there, or perhaps present it both ways. And consider, I mentioned maybe highlight it. Consider that presenting it both ways is highlighting it. I might say this is the mean salary without Michael Jordan, and this is the mean salary with Michael Jordan. Like these are the two different cases, and this is the effect of that outlier. I'll note that there are other statistical methods that account for outliers. So you'll see things like a trimmed mean or robust regression. There's a lot of them. There's textbooks out on these things. My opinion, I actually just finished a textbook on reading through a monograph on robust regression, and I think it's got some trade-offs, honestly. These are available, but I guess I'd tend to lean against them for non-experts. I think a better solution is to present it with and without the outliers to show both and present a statistic that you understand, like a classic mean. And I guess the reason I prefer that to using some of these outlier-resistant methods, quote unquote, is that the story that the fancy methods tell is not necessarily the story of the original methods. Like a trimmed mean isn't the same thing as a mean. A robust regression isn't the same thing as a regression. These attempt to lean towards the center mass, the main chunk of data. And that can be good, but it has some interesting ramifications regarding the story that's you're telling and the actual question that you're answering. So if you see those things, they're not necessarily bad. In fact, they can be good in the right context. But as a rule, unless you really understand them, I recommend not doing it. And one of the reasons I recommend not doing it and instead presenting it both ways is when you present it both ways, you can present statistics you understand. And if you don't understand these, it's going to be difficult, if not impossible, to really tell the story, because you're going to be telling a story based on or using tools or using evidence that you yourself don't understand. And these methods are not necessarily easy to understand in terms of what the implications are, et cetera. Now, suffice it to say, there are some who disagree with me and who think everybody should use a trimmed mean instead of a regular mean. And absolutely this should be done by individuals, whether they understand it or not. So I'll note that those individuals are out there and that there's differing perspectives here. But if you're looking at data with outliers and you've gone through these steps and you end up at this last bullet point, I recommend running your analysis, keeping them in, and telling it both ways. Now, or telling it both ways. Maybe both ways. I'd lean towards keeping it in. It's up to you whether you do it both ways or not. I will say, in my experience, most outliers fall in the first two bullet points. The either it was a typo or it's a subgroup that we didn't account for at the beginning of the study. Yes, most outliers in my experience are in one of those two classifications. I will say that if it gets the third classification, in several cases, if not the majority of cases, I actually think it probably is a subgroup. I just didn't have the data to identify the subgroup. So maybe I just collected data on the outcome, but I didn't collect data on demographics like sex or race or something like that. And I'm thinking of several examples. So I'll even say if half of the time it gets to the last bullet point that I have to keep it in, I suspect there may be a subgroup at play. On the other hand, there definitely are times too where I'm analyzing data and there's just an outlier. There's just one individual who's way different, or who's largely different. It's not necessarily as drastic as Michael Jordan's income compared to the rest of us. But there's one individual who has different scores, and it's important to keep that in because it's important to acknowledge that variability, and that for those types of individuals, the models or the statistics may not be a good fit, and to increase our standard errors and account for that within our standard errors. So that can be important. All right, inferential statistics. So I will say there are two reasons There are two things that I really like about this lecture set and that really caused me to move in this direction as opposed to a different one. I was thinking maybe a more classical, um, uh, lecture set on that. It probably just would have been on graphing or something like that. And one of the reasons, one of the two big reasons, one of them is graphing, that I wanted to do this and the ways in which we use graphics. The other one is the discussion of inferential statistics. We just finished a whole lecture set last week on inferential statistics. And clearly, as we saw, inferential statistics has a role to play in storytelling. But I don't think it's always clear what this role is in storytelling. We kind of focus a lot on the kind of the craft of inferential statistics, like how do we do it, almost the how, and we don't focus a lot on like what does this mean, and we've spent a lot of time talking about what it means, but even then, like what role does it play in the broader story? I think we don't always get a lot of that. So this is one of the biggest components of this entire lecture set this week that I'm the most excited about talking about, and it is what role is it that inferential statistics do? And here it is in a bullet point. Inference is the process of moving from a sample to a population. So I have a sample. I want to make decisions about a population. This is where inference comes into play. And what's funny about this is that's really it. Like we do a lot of work on inferential statistics. And frankly, most of the field of statistics is crafted around inferential statistics. Not a lot of work on descriptive statistics, believe it or not. It's all inferential. And it's because this is a good and important question. We often have samples. We often want to make decisions about populations. How do we do this? But when it comes to storytelling, sometimes this isn't a main part of the story, or even if it is a main part of the story, not every part of the story relates to this. And it's important to realize this is all inferential statistics is. It's really only important if I don't have the population data and I want to make population conclusions. And if that's not the case, then this isn't something that is really useful. I recently saw a report that was put out with population level data, and they did a confidence interval, which is an inferential statistical procedure. And somebody asked me about this. They said, well, am I missing something? What's the use of a confidence interval here? I said, well, maybe they want to do future prediction, and so then we don't. And then the presenter actually said, yeah, this isn't for future prediction. And the person who asked me about this laughed. Okay, so in that case, a confidence interval, an inferential statistical procedure, when you have population level data, is literally meaningless. It's unnecessary. It adds an interval estimation, this measure of uncertainty, to a population data point of which we are certain about. So in that case, inferential statistics doesn't have a place. Similarly, even if I'm using a sample, if I'm not trying to make population level conclusions, inferential statistics doesn't have a place. I'm just trying to describe what happened in my sample. Well, use your descriptive statistics. I find sometimes that when doing reporting, people feel like they have to be fancy. I have some clients who will say, can't we do anything fancier than this? And the answer is always yes. Like, oh, absolutely, we can do fancier stuff. You just don't need to. If I'm trying to describe a sample and I calculate the mean age or median injury severity score, or I calculate some percentages, the percentage of male and the percentage of female individuals who are in our population or who are in our sample. If I'm just describing the sample and what happened, I don't need to do anything more than that. That's it. If you're just describing what happened, use descriptive statistics. Inferential statistics don't have a place. Inferential statistics have a place where you are trying to extend your claims from the sample to other people you haven't studied yet, to, in other words, the population. And there's a lot based on study design. We'll go into study design later in this lecture set. So there's a lot based in there onto the legitimacy of that expansion. But statistically, the legitimacy of that expansion is based on the use of inferential statistics. So that's what inferential statistics support. That's where you use p-values. That's where you use hypothesis tests. That's where you use confidence intervals, is when you are trying to take data from a sample and make claims about individuals that weren't in the sample, or make claims or implications even about the broader population. That is the role of inferential statistics in statistical storytelling. So when I'm talking about this, I may drop in, and often inferential statistics I use sparingly. I'll do it when addressing a main research question. I'm trying to assess whether or not individuals in a particular, this is a recent contract, we have individuals in a patient protocol who were studying an outpatient procedure support system for these particular patients. Very cool idea. Goal is to save the hospital potentially millions, if this works, of dollars in staff time on from patients who are coming in cases where they shouldn't be coming into the hospital. So not just staff time, but total overhead, over care. And in this particular case, we're looking at, again, the amount of times these participants come in versus participants who aren't participating in the program, and trying to study that. Now, I'm going to use a lot of descriptive statistics to talk about the participants who are in the study. The ages of the participants, the sex, gender of the participants, races of participants, classifications of their injuries, previous treatment received at the hospital, et cetera, et cetera, et cetera. I really want to be clear about describing this, but none of this stuff am I trying to apply to a broader population. I'm just saying this is what happened. I'm not trying to imply that this proves that 42% of our patients are female because 42% of the sample is female. That's not the reason I'm including that. And again, go back to storytelling. What's the reason you're doing this? I'm doing this so that you can see who was in our study, so that you can think about, well, does that match who you're working with? And if so, then maybe the study results may apply to your study. We'll get there later when we get to study design as a part of statistical storytelling. But I'm not trying to make an implication about the population. On the other hand, when it comes to how effective the program was, there I am trying to make an implication about the population represented by my sample. And what I'm going to do there then is use inferential statistics, because I want to say this program worked. And I don't just have evidence that worked in the sample. That would be descriptive statistics. On average, our patients were in the hospital 13% less. That would be descriptive. I want to say there is reason to believe that on average, patients who participate in our program will be in the hospital less. That's the claim I want to say. And I want to say patients who participate in our program will be in the hospital less. If we do this with patients in the future, this will keep patients out of the hospital. The other thing I want to say is if we do this with patients at other location, we have reason to believe this could keep patients out of the hospital, so long as we're doing it at locations with populations represented by our sample. And maybe stretching it a bit further beyond our inferential statistics, but in a very practical way, maybe this is worth trying with other populations not represented by our sample, because it does work for our sample. So this is a promising practice to continue to investigate. Again, when to use, when to not use inferential statistics. I use them when trying to make claims that I want to extend beyond my sample. There's a bunch of calculations that we make that I don't really care about that for. Things that are describing my sample, descriptive statistics, demographics, what happened. And in medical reports, and if I'm presenting to C-suite or something, sometimes, or maybe all of the statistics I present are descriptive. That's not bad. It depends on your goal. It's not bad to present mostly descriptive statistics. But whenever I want to take information from a sample and I want to use it to say that X was effective, or we can anticipate to see this relationship, and I want to say that regarding individuals who are not individuals that I have talked to in my research. That is where inferential statistics come into play. So within inferential statistics, remember we had two different approaches and two different goals. Our first approach we had as hypothesis testing. And with this, we had a null hypothesis, and then we ultimately tested our data compatibility with the null hypothesis. It's the p-value, pretty much, is the compatibility between the data and the null hypothesis. And the smaller the p-value, the more incompatible they were. And we said, if I'm going to get rid of one thing, be it data or my presupposition without knowing any data at all, well, I'm going to trust my data and I'm going to get rid of my presuppositions. So that's the process of hypothesis testing. And then we had confidence intervals, where we found reasonable ranges for population parameters. But ultimately, again, our goal is to use with inferential statistics, is to use them in the times where we are using data from our sample to make decisions about the population. That's when we use inferential statistics. I will say the risk. What's wrong if I demographics? Percent male, average age. Let's say I use percent male. What's wrong if I use inferential statistics on percent male? It just confuses the issue. It's statistically significant. What does that mean? And ultimately, it doesn't necessarily mean anything. And of course, if you have a whole bunch of statistical significant results that don't actually mean anything, it'll be difficult to communicate the ones that do mean something, and difficult to communicate why some mean something and some don't. Again, the goal is to present a clear story or a clear argument as we're telling our statistical story. And so when you hear me talk about the purpose of inferential statistics, really think through, do I need them? I would say lean to descriptive statistics if you're using numerical or quantitative summaries. And then if you're looking to make claims regarding the population from sample data, or again, looking to make claims beyond the individuals in your sample, that's when you would use your inferential statistics. It's important to remember that when we're doing inferential statistics, when we're using data to construct a new hypothesis, ultimately, all of our hard work, all of our math, all the study is to get a more accurate guess as to what the population value is. That's it. And we talked about this in the previous lecture video too. The guess, and when thinking about this, think about it as the same way as any other guess, though maybe it should be given a little bit more respect than an off-the-cuff hypothesis about what the population values are, or, and when you hear me say what the population values are, think, when I'm comparing two programs, does program A work better than program B? That'd be a population claim as regarding the whole program, not just a particular sample studied with that, regarding the program in general and participants in the program in general. Those are population claims. So when I make claims about the population with inferential statistics, it is something that I've done with fidelity, and if you've done all the work behind it, it's a good guess. But don't forget, it's making an educated guess, but a guess at what the population values are. I say this because it's important when you do that to observe and evaluate moving forward. It's kind of like the accept uncertainty principle we talked about in the first video. It's accepting the fact that even with my best attempts, my guess might be wrong. And because of that, I don't just close my eyes and sing la 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 after I've made my decision. I continue to evaluate the effectiveness of that. I love this quote by Milton Friedman because ultimately it gets to the heart of statistical storytelling and ultimately statistical decision making. And that is, the real measure of whether the guess was right or not isn't the amount of statistics that went into it. The real measure as to whether the guess was right or not is if it turns out to have been right. Right? Pay attention to it. If it's working, great. It was the right decision. If it's not working, well, then consider that maybe it was the wrong decision. As we mentioned in the first video, there's no closed door questions in statistics. We just have evidence. And so don't close your eyes to future evidence. And especially after you've made a decision, pay close attention. Even if it was well studied, well supported, it doesn't necessarily mean that in the moment you should have done something different if all of the evidence pointed in one direction. But pay attention to how it worked out to make sure that that was actually the right decision. Again, I have seen clients, truly I have seen this, who will, well, we followed the data and then kind of close their eyes to everything that happens afterwards. And that is not a healthy approach. It's not a healthy way to practice administration. It's not a healthy way to practice medicine. All right, statistical significance. Again, statistical significance is the term that we had for rejecting the null hypothesis in our hypothesis testing. And this gives some evidence that the null was incorrect about the population. So remember, we had a null. Sometimes it was that the mean of the population represented by my sample is, a classic value, even though I've changed the program. It's the population represented by my sample hasn't changed at all, even though my sample got some new cool program. And we talked about one potential flaw in this earlier, or the place of this, I should say, earlier. But here, I want to emphasize a potential flaw in this, and that is it goes as far as it goes, but it doesn't go further. So this is really useful for determining characteristics about the population, but it doesn't really give you value. It doesn't really even describe how big the effect was. Now, some people think this p-value or the test statistic, hey, this test statistic is even further out. That means it must have an even bigger effect. That's actually not true. The test statistic can be very, very, very far out, and the effect can be very small. Similarly, there's a lot going on within situations that test statistics and inferential statistics in general aren't accounting for. Hey, yeah, maybe it would be better to do policy A. Unfortunately, everybody hates policy A. So that's just really not going to happen at our institution. Well, to make a decision to implement policy A because statistics told me so, it's going to turn out that policy A was a really bad idea if everybody is against it and wants it to fail. Turns out that maybe in an environment that I studied it in where everybody liked it, it works well. And in an environment where everybody hates it, maybe it doesn't work very well. Maybe I want to implement a cost-saving procedure. And I did a study to determine if this will actually save costs, and it turns out that it will long-term. And then I want to make the decision now to implement that. But it's a really costly changeover. I have to pay a lot of money for new equipment. I have to pay a lot of money for new training. Is that the right decision? Well, statistics doesn't help you make that decision. Inferential statistics is something that can help determine, was it actually cost saving at the population level? Could you anticipate that it would be cost saving moving forward outside of your sample? Inferential statistics can help with that, but it can't help say, based on your company or hospital or group's financial situation currently, this is the right move. And this goes to one of our points in the previous lecture, be thoughtful, but it also highlights one of the limitations of statistical significance in storytelling. It really is just about the relationship between the sample and the population, and using sample data to test a claim about population data, or using sample data to come up with an interval for a population statistic. But it doesn't go further than that. And a lot of times people engaging in statistical storytelling sometimes blur the lines inappropriately. by implying that some of these judgment calls were statistic, or this was implied by the statistical procedure, or this is really what the statistics say we need to do. In the cost-saving measure, you may hear somebody say, well, the statistics say this is going to save us money. Yeah, but they don't say this is the right move for us to do right now. And that distinction is important and subtle. So significance has a big, important place here. It moves from sample to population, but it also has some limitations. The size of the observed effects is actually a big, important component. And it's something that more and more recently, as we implement statistical reporting and storytelling, we are recommending for practitioners to use. Formally, this is called an effect size. It's a bit of a buzzword, but it's something that is an important addition to provide with statistical significance and inferential statistics. So effect size, the buzzword, really just refers to the size of the effect. Sometimes you'll hear this referred to as practical significance. Another thing, especially in the medical setting, you'll hear is clinical significance. Are these results clinically significant? There's a bunch of calculations for effect size, quote unquote. Again, it's a buzzword. Everybody's got their own effect size that they like. Cohen's d, eta squared, partial eta squared, modified partial eta squared, generalized eta squared, a lot of eta squareds, r squared, adjusted r squared. Like there's a bunch of them. Depending on the particular tests, there are some that are more common than others. But for me, I actually really like to keep it simple when possible. So let's say I'm doing a program to reduce smoking. I really like how many cigarettes less are the people in my program smoking than the comparison group. That number of cigarettes could be considered an effect size. I like this because it really highlights what we're trying to study. With a lot of the fancy ones that you'll see and read about, the interpretations of them are lost on 99% of individuals who are using them and 100% of the individuals who are reading about it, especially in a practitioner audience. But when we keep it simple, effect sizes are just how big of a difference or how large of a relationship we saw, depending on if my research question is assessing differences between groups or relationships between variables. And quantifying that in a way that individuals can see, this can be really helpful. I will say, in defense of formal statistical calculation or the fancy effect sizes, the number of cigarettes difference is a mean difference, and we talked previously about the risks of just reporting a mean as opposed to reporting a measure of center and a measure of spread. The other fancier calculations mix together measure of center and spread to create standardized effect sizes that account for both. But for me, I really like reporting simple effect sizes, like how big was the change? How many, in terms of number of cigarettes we've reduced per person per day, how effective was the program? Now, it's important to realize that statistically significant doesn't imply practically significant, nor vice versa. And this is a mistake that many, many people make when looking at statistics and when telling statistical stories, and frankly, when consuming statistical stories. We like to say things were statistically significant and then end there as if that then implies that they were practically significant. This is not true necessarily. Sometimes it's true, sometimes it's not true. And because of that, it's not necessarily true. We can't assume that connection. And this isn't just a kind of a mathematical triviality where I can randomly pluck a case out of the sky with an infinite sample size, and then that makes this not true. No, in very real ways, in very common situations, these don't necessarily support one another. That statistical significance and practical significance are not the same thing and don't necessarily imply one another. Now, typically what the workflow is going to look like is that after we have statistically significant results, we then look at their practical significance, and done in that order. And these are typically presented hand in hand. Again, it's become a big push in the statistical community that these be presented hand in hand because of that third bullet point there, that they don't imply one another. So let's actually real quick consider one without the other. So let's consider statistical significance without practical significance. Probably, again, the most missed direction in that in statistical storytelling, people will present statistically significant results and assume that that means practically significant. That tends to be how this goes. So what this means is we have evidence that the relationship isn't due to random chance. That's what statistical significant means. That the difference between groups isn't just due to random chance, or that the relationship between variables isn't just due to random chance. But it's not practically significant. So that means that the size of the difference or the size of the relationship isn't large enough to really mean anything clinically or practically. In my smoking example, think of a program that has a quote-unquote statistically significant effect, but that the size of the drop of the people who participate in my program, they smoke less cigarettes than the people who were in the control. The size of that drop is 0.001 cigarettes per person per day, like a fraction of a fraction of a fraction of a cigarette per person per day. While that, in that case, is statistically significant, practically that is meaninglessly small. So that is not really useful. As a bit of an aside, there's been some discussions of moving the statistical significance testing instead of having a difference of 0 to tests about having a difference that is the lowest meaningful value, so that when you have a statistically significant effect, it says it's statistically significantly greater than the lowest meaningful value, so you know that it's useful. But that's a bit besides this point here. That is certainly very, very, very uncommon, at least in the modern statistical and research sphere. And so we have to have this discussion that again, we can have statistically significant effects and have a program effect be 0.0001. And it turned out to be statistically significant, but practically that difference is absolutely meaningless. And again, we call that practically insignificant or clinically insignificant. When does this happen? And yes, this does happen. This happens all the time. When does this happen? Usually this happens when we have very, very, very large sample sizes. Recall, as the sample size increase, the standard error, that's the standard deviation of that sampling distribution of the mean, gets very, very, very small. So we're able to statistically detect very small differences. So when we have very large sample sizes, this distinction becomes extraordinarily important, because that tends to be when we have statistically significant results that do not imply practically significant or clinically significant results. All right, let's consider the other direction. Practically significant without statistically significant. This doesn't happen as often, but sometimes people will kind of discover, quote unquote, this and be like, oh my gosh, look at this. So this will happen. I'll be presenting a data set, and there will be a really, really big difference. Oh my gosh, look, the number of cigarettes dropped 10 cigarettes per person per day. That's half a pack a day. This is an amazing program. And if so that might be practically or clinically significant, but in this case, it would be without statistical significance. So what would that mean? That would mean that, hey, half a pack a day, that means something. That'd be really good. On the other hand, because it's not statistically significant, I don't have evidence that this is anything other than random chance. It's kind of interesting to think about. How can you have such a large effect without that evidence? And it doesn't happen as often, but it does absolutely happen. And again, what I have to look at is it statistically significant? If not, I don't have evidence that this is anything other than random chance. Now, though this one doesn't happen as often, what you'll see happen here is people will say, oh, but look how big it is. Look at how big that effect is. Oh man, well, I know it's not statistically significant, and all those statistician killjoys just don't want to do it because it's not statistically significant. But look how big effect that is. That'd be so great to actually use. And the problem is, again, as we saw earlier, when we say it's not statistically significant, what we mean is this could very well have come from a population where there's no difference at all. And it seems counterintuitive. This is why we run the statistics. It seems counterintuitive that we could have such a big difference in our sample that could reasonably have come from a population where there's no difference at all between the treatment and control. But that's what a lack of statistical significance in a finding means, is that we don't have that evidence to say we think this is more than chance. And ultimately, that means that I don't know that that effect is really there in the population. I don't know that there's any effect there in the population. That's what the lack of statistical significance means. So ultimately, in that case where we have massive practical significance but no statistical significance, we're back at square one. We don't have evidence to conclude that this was anything more than random chance. We don't have any evidence that the treatment and control are different. Again, we have that massive effect size number, that massive practically significant number, but we don't have enough evidence to conclude that that happened outside of chance. Now, again, this one is less likely. So how does this one happen, or when does this one typically happen? Typically, this happens when we have very, very, very small sample sizes, and when the variance is large. So when the standard error is very large, we just aren't able to determine statistical significance, and we have a small sample size. We aren't able to determine statistical significance even with large effects. So that's when you'll see this, is with smaller sample sizes, with large individual population variances. You may see a large, practically significant effect that is not statistically significant. And those ones, are ones that we don't have evidence to believe that even though it looks practically significant, that isn't just smoke and mirrors, that actually means anything. We need both of these together. So we look for statistical significance first, to make sure that we have evidence to believe that there's a difference between the groups in the population, or that we have evidence to believe that there's a relationship between the two variables in the population, depending on whether we're doing difference or relationship. And then I'm just going to do difference between groups, because that's easier for me to think about, maybe easier for you. And just know that relationship between variables is the same thing. You can plug it in when appropriate if you want to. So we make sure we have evidence to believe that there's a difference between groups in the population. And then once we know that, then we can look at that effect size to see how big we think that difference might be, and make sure that that effect size is practically significant. Note, we can kind of combine this with confidence intervals. They're a bit of a mix of both. Remember, we can use confidence intervals for testing, but confidence intervals also talk about the estimated size where we think the population value might be. So we could use a confidence interval to say, well, how big do we think this difference is in terms of the number of cigarettes? If so, we'd want both ends of the confidence interval to be in the practically or clinically significant range. So for instance, if I have a confidence interval that's statistically significant, that is that there's a difference outside of zero, that might be from 0.0001 to 0.0005, which means that that's the number of cigarettes less my group smokes, and that isn't meaningful at all. Of course, it might also be from 0.001 to 100, and 100 would be great. 0.001 would be terrible, and I don't know if it's practically meaningful or practically unmeaningful, so that doesn't really help me either. With a confidence interval, I'd like to see both ends of the confidence interval be practically significant. So maybe 5 to 10 cigarettes is my confidence interval. 5 is a little low, but it's still practically meaningful. 10 is right around where I want to be. So I'm somewhere between, I'm definitely practically meaningful, definitely clinically significant, but maybe I'm somewhere between a low and medium clinical significance in that confidence interval. That's what I'd aim for here. All right, balancing with utility. So there's another concept that classical testing doesn't really cover, and that is this external context concept. Even if the effect is statistically and practically significant or clinically significant, practical significance, clinical significance, but cost time prohibitive, it might not be worth it. So in this case, again, that impact or what it costs that's not really addressed by classical statistical tests. We mentioned this example earlier, a cost-saving policy measure that might save costs in the long run, and we have evidence that this will continue to do so in the population, but in the short run is going to cost a lot more. Is that really worth it? And that's not an answer statistics can give. We can't use statistics to say, is that worth it for you, your company, your situation? That's a human decision. That's a judgment call. Statistics on the question of did this save costs can tell you yes or no, but it can't say, is that cost saving worth it? Is it worth the implementation? Is it worth the headache for our staff? Is it robust to long-term changes in the economy? Blah, blah, blah. This is all stuff that our statistics, maybe that last one, statistics could help with a little bit, but the rest of them, statistics can't really help with that. Certainly not statistics on did this save costs and the impact of, based on the sample, do we think it'll save costs in the population moving forward? Now, I mention this because it's important to remember that when you deal with these types of judgment calls, you need to treat them and report them distinctly. So when we're telling our statistical story, it's important to be clear about the type of evidence that we have for our claims. Sometimes I'll see these types of judgment calls mixed in with evidence of inferential statistics. And individuals who are presenting this will use arguments that are made for inferential statistics next to their judgment call, low-key implying that the judgment call is supported by those arguments for inferential statistics when that's not at all true. So it's important to be really clear and distinct when you're talking about moving from a sample to a population, which is something that inferential statistics can help with for a particular question and when for a population that's represented by the sample. And then if you have to make a judgment call, so that might say this, I have reason to believe this will save X amount of dollars on average moving forward. Or confidence interval. It'll say between $100 and $200 per patient. That'd be great. And then your judgment call is, I think we should do this. Those are two different types of claims. The first one, how much money we'd save using inferential statistics based on sample data to make an educated guess about population data. That is statistics. Then I think we should do this. That is judgment. And it's important to distinguish between those. There's a lot of decisions. Ultimately, statistics, again, are a tool. They are a tool, they are a helper, but they are not good at decision-making. They're actually pretty bad for decision-making because there's always context to decisions. And that's what I mean here when I say balance with utility in the title of this slide, that you have to balance the statistical contribution to your decision with the utility of the decision and the statistic within that context. What's going on? What's going to happen if we decide A or B? What are the risks associated with A or B? These are things that statistics don't know and in many ways can't know, but are all just as important to consider when making a decision as the statistic itself. All right, descriptive statistics. And I think this is our last one. This has gone a little long as well, so thanks for sticking with me. Don't forget about descriptive statistics. It might seem like, again, with inferential statistics, making decisions, doing intervals for population and stuff, that we've kind of graduated. Oh man, when we started with descriptive statistics, just to build up to inferential statistics, because now we're talking about populations. And there's no place for there's no place for descriptive statistics. But nothing is further from the truth. Descriptive statistics are fantastic for describing a sample context. Recall all of our stuff is, inferential stuff is based on the population represented by that sample. So who's represented by the sample? Well, let's talk about what the sample demographics are, and that can help you get a feel for what population is represented by them. Describing observed effects. Effect sizes. Yes, effect sizes are descriptive. We are describing the size of the effect we observed in our study. It's important to consider some implications here. Effect sizes are not for the population. They are only for the sample. There's a 50-50 chance a future study done in the exact same way with a different sample from the exact same population would find a smaller effect, and 50-50 chance it'd find a larger effect. In fact, even assuming that the effect size that you found for the sample is exactly true for the population, there's still a 50-50 chance that if someone ran this study again, they would find a smaller versus larger effect size. So effect sizes are absolutely descriptive and fantastic tools, again, to give context to statistically significant claims made from inferential statistics. Just what does that mean? And what impacts can that have? And more. Descriptive statistics are, again, fantastic. I think they're a bread and butter tool. I think they get a bit of a bad rep, and sometimes rightly so. People will use descriptive statistics to make inferential claims, and that is not their purpose. They're actually really bad at that. I can't assume that just because something happened, that means it will happen again. I can't assume that just because something happened with one small group, that means it would happen with a different group. Those are bad assumptions, and descriptive statistics offer bad evidence for inferential questions. What descriptive statistics do well, however, is to describe. Descriptive, it's in the name, to describe what happened and what is happening, and they are excellent for that. Inferential statistics really are never presented without descriptive counterparts. If I'm studying the difference between two groups, I'm going to present the mean and the standard deviation of group A and group B. If I'm studying data over time, I'm going to present the mean and standard deviation of data at the pre, at the post, and the follow-up, or perhaps mean and interquartile range if I'm dealing with data where I want to represent the 50th percentile rather than the mean. So all of my inferential statistics are going to have these descriptive counterparts associated with them. And again, it's important to not forget or think less of descriptive statistics now that we've got the inferential stuff. Again, they remain our bread and butter, and it might be that most of the statistics that you present in a paper, potentially 80, 90%, sometimes in some presentations or reports you make, maybe even 100% of statistics may be descriptive. But when we think about it, again, think about what the purpose is of the inclusion here. Descriptive statistics are good for describing what happened, but very bad for implying that this will happen again. That's what inferential statistics are for, or for implying that this would be true with a different population or at a different site, or with a different sample. All of those things are what inferential statistics are for. But when describing what happened and helping to explain, descriptive statistics are fantastic. And actually, one of my favorite descriptive statistics is what we're going to be talking about in the next video. It's something that not many people think of as a descriptive technique. In fact, most people don't think of it as a descriptive technique, but it's a descriptive statistic or a descriptive summary of data. And it's one of my favorite things to include in the second main point of this lecture set. So thanks for sticking with me as we talk through statistics. Now we're going to jump into this next component, and we'll dive into the next video.